of electrical circuits, especially the circuit elements, wherein today we'll discuss the interconnections. The interconnections have a big role to play in determining the working of the elements when they act together. Especially when you look at the inductors, the problem happens to be that when you're having a pair, they can be conductively connected or not. Like in a transformer, they are not. Though the reference voltages can be made the same if you are connecting the lower part of the terminals together. However, when they are conductively connected, we have two types of connections. We have the series connection as also the parallel connection. And within both these connections, we have the fluxes aiding each other or opposing each other. When the fluxes are aiding each other, then what happens is that the totality of the inductance, which is the reaction of the pair of coils, increases in both the parallel connection as also in the series connection. So these are some of the theory aspects. So let's move on to some of the problems. Of course, we start with the capacitor, and it is interesting to note that though we have a pair of capacitors there, the switches perhaps have a role to play in either connecting them in parallel or leaving them in series. We also have a 3-volt source feeding the arrangement. In the figure shown, all elements used are ideal. Of course, unless they are ideal, we will have problems for solution. For time t greater than less than 0, S1 remains closed. So in the beginning, the source is feeding the capacitor, at least capacitor C1. Okay. And S2 remains open. So it's feeding the capacitor and filling it with charges until it opens up. Okay, once it's fully charged to the full voltage, that is 3 volts. And S2 is closed. Okay, at t equal to 0, S1 is opened and S2 is closed. If the voltage VC2 across the capacitor VC2 at t equal to 0 is 0, the voltage across the capacitor combination at t equal to 0 plus. Okay, so the most important aspect here is that whatever be the connection, it is constant charge theorem, or in other words, the charges cannot go suddenly. So we have what is called as the entire voltage. The voltage cannot disappear suddenly. So the entire voltage is still available at t equal to 0 plus. Thereafter, that is 3 volts. Thereafter, it peters down by sharing, and then the capacitors now become a series in nature. Right at this point of time, they are of course series because of the connection, but at the same time, this voltage is in series with the two capacitors. Okay. And when you are having series capacitors, it's going to be 1 into 2 divided by 1 plus 2 by 3. Okay, so it's a different situation altogether later on. Okay, moving on to question number 2. It's having it is having a cable. Okay, so we have two single core power cables have total conductor resistance of 0.7 ohms and 0.5 ohms respectively. So this is here we talk about the copper content or the aluminum content if it is all aluminum conductor. Okay, and this is also applicable to triple AC, that is all aluminum armored conductor. Okay, so that is aluminum. Okay, so that's one thing, but then at the same time, and the insulation resistances, so it's a cable, so we have what is called as a covering for it, which gives rise to capacitance, and the capacitance also has discharge possibility, so we have resistance also, and that's what is called as the insulation resistance between core and sheath. So the core is the conducting material, the sheath is the armor that is laid in the ground. Okay, 600 mega ohm and 900 mega ohm respectively. Obviously, they are of large values. Okay, since they are insulators. When the two cables are joined in series, now we are having two cables in series where the conducting materials are connected together in series, but at the same time, the insulating materials are now connected in parallel, because all these resistances are with respect of the conductor with respect to the ground where the cables are laid. Okay, so we now have a different picture. And the question is, when the two cables are joined in series, the ratio of insulation resistance. So 600 parallel 900. Okay, and to the conductor resistance to 0.5 in series with 0.7. Okay, so it comes to 300 into 10 raised to 6. Okay, because we have on the numerator megohms being considered. Okay, so moving on to an array of inductors, as was mentioned earlier. We have done such problems even earlier, but at the same time we'll use an easy pattern this time, where we see current entry at dotted terminals in two coils would indicate that the inductance would be the mutual inductance would be doubled and added. Okay. On the other hand, if current entry is on the dotted and the current exit is on the undotted terminal of a pair of coils, or vice versa, then we are having a situation wherein the mutual inductance will be doubled, but then of course it will be negated or reduced from the total effect. Okay, so let's do it in the same manner. We have in the third problem, the effective impedance or in terms of reactances will be given by J5 plus J2 plus J2, that is J9, and then from there we will remove the mutual inductance or add the mutual inductances by doubling them. Okay, so we have in the coil number 1 and 3, J5 and J2 are linked via a mutual inductance of J10, but then the current is exiting the dotted terminal and entering the dotted terminal of one coil with respect to another. So we see that we have a minus J20 coming into the picture. Okay. Then again, when you look at coil 2 and coil 3, they are again connected together inductively. So we have J10 between them, but at the same time current is entering both the coils via the dotted terminal. So we have plus J20 coming. So and these two cancel, and so we have J9 left. Okay. Problem number 4. Here, of course, all the three coils have mutual inductances, unlike in the problem 3, where we do not have mutual inductance between coil number 1 and 2. Okay, so as before, the procedure is to add together the self inductances. So 4 and 5, 9 and 6, 15. Okay, and then the coil 1, 2. It is entry at dotted and exit at exit at dotted with respect to coil number 1 and 2, or 4 Henry and 5 Henry. So we'll talk in Henry this time, unlike in the earlier case. So we have minus 2 Henry as the mutual inductance contribution, and then between 1 and 3 we have 3 Henry, and current enters the dotted and exits the undotted terminal with respect to the two coils. So we have minus 6. And with respect for the coil number 2 and 3, it is 2 Henry, so it's 4 Henry. But at the same time, it is it can be seen that the current exits via the dotted terminals for both the coils. So we are having a plus 4 in this case. Okay, so everything added together, that is plus 4 minus 6 and minus 2 plus 4 and 5, 9 and 6, 15 gives you 11 Henry. Okay, so it's now in Henry. Okay, moving on to problem number 5. Okay, so it can be seen that there is 18 ohms, a capacitance of capacitive reactance of minus J12, and then two inductances J2 and J8 with mutual coupling. Okay, so obviously Jm is going to be equal to 8 to the 16, the square root of 8 to the 16, that is 4, but of course with K also into the picture. Okay, so let's read in the series circuit shown in figure for series resonance. Okay, which means that only 18 ohms remains. Minus J12 is going to be cancelled with respect to the inductive reactances. Okay, the coefficient of coupling is asked. So we see that we have to have L1 plus L2 plus 2m as equal to, or minus 2m as equal to minus J12. Okay, as equal to J12. Okay, such that, okay. So now 16 is already there, so you have to remove 8 into 10 is already there, so we have to add a 2. So it's going to be K is equal to is going to be equal to 1 by 4, such that the effect of the mutual inductance is additive in nature. Okay, so we have 0.25 as the answer. Okay, sixth problem. Three coils, okay, coupled together, and we have 4 plus 4 plus 4, 12 Henry as the contribution of self-inductances. Mutually, we have coil number 1 and 2, minus 4 Henry, and then we have between coil 1 and 3, it is minus 2 Henry, and between coil 2 and 3 it is going to be plus 2 Henry. Okay, so everything put together we are having 8 Henry as the overall inductive reactances. Okay, so let's move on to a different setup where we are having capacitors connected together. But then though we had discussed a few aspects, okay, what we are going to discuss here will be a little different. Okay, mostly the practical aspects of connecting capacitors together. Okay, so let's see the first, let's look at the seventh problem with C2 C3 in series parallel to C1. Okay, so that's the setup, and the reading goes that three capacitors C1, C2 and C3. So I suppose we realize that C1 is the one in parallel. Okay, whose values are 10 microfarad. So 10 microfarad in parallel to 5 and 2 in series. Okay, respectively have breakdown voltages of 10 volt, 5 volt and 2 volt. So obviously we can't have 10 volt being given there, because the 2 microfarad capacitor can stand or withstand only 2 voltage. Okay, and if you give, and when you are having capacitances in series, we realize that the voltage division will be proportional to their reciprocal. So it's going to be a huge voltage. You can't have 10 volt. You can't have you can't even have a voltage as large as 5 volt, because again 5 volt, when you divide it between the two, so we'll have a problem. Okay, so let's read further. Have breakdown voltage of 10 volt, 5 volt and 2 volts respectively. For the interconnection shown below, the maximum saved voltage in volts that can be applied across the combination and the corresponding total charge in microcoulomb stored in the effective capacitance. Okay, so CV equal to Q is one way, and then you have the different answers. So when you are having the different answers, it's best to see that CV should be equal to Q. Okay, so we can find out the total effective capacitance very easily, because it is 10 parallel, 5 and 2 in series. So 5 and 2 in series is 5 to the 10 by 7. 10 by 7, when you add to 10 microfarad, it is the same as equal to 80 by 7. So 80 by 7 is going to be multiplied to the voltage, okay, such that you get the total charge. Okay, so we and of course it's in microfarad, so you'll get it in microcoulomb. Okay, so as simple as that. So of the four of the voltages that are shown, 2.8 and 7, obviously 7 is ruled out, because that would give rise to a voltage across the capacitor C3 as given by 7 by 7 multiplied by 5. So you'll have 5 volts, which it will not be able to withstand. So the bottom voltages, that is options B and D, are removed, and of A and from amongst A and C, you can just simply multiply 2.8 by 80 by 7 and see if you're getting the required charges, and you see that answer C is better. Okay, it's of course the only correct version. Okay, moving on to problem number 8, where we see a practical situation wherein the cables, okay, represented by R, Y and B will have capacitances, and these capacitances are connected to each other in a similar configuration. Okay, so when you are giving such a configuration, I suggest that you have a common line for Y, a common line for B and a common line for B, and then connect them together. So we also see that R is now the grounded portion. So R is grounded, okay, and it to R is connected CS from Y, CS from B, as also CS from CS from Y, as also from CS from B, as is shown in the figure nearby, and also to R is connected CC from B, as also from Y. Okay, so we have a structure like this as shown alongside, and so we see that CC is now in parallel with two capacitance blocks in series. The first block, both the blocks have CC and CS in parallel. Okay, so put together, you realize that it's going to be CC and CS in parallel. That is CC plus CS. CC and CS in parallel. So it's CC plus CS by 2. And in parallel means multiply by 2, and then when you divide the combination, again it's going to be half. Okay, and then you add to CC, so together it becomes the same as equal to 3 by 2 CC and CS by 2. So C is the answer. Okay, So finally, we move on to some kind of consolidation in these areas. We have problem number 9. We see the current picture and the voltage waveform. Since they are both plotted with respect to time, first is a triangle which tells us that 2 amps to 2 amps is the current is rising in 25 seconds or microseconds or whatever. Okay, let's say it's seconds to 2 amps. Okay, and voltage remains steady till then. Okay, so this definitely tells us that when you're taking the differential with respect to the curve number 1, that is of the IT, then you get what is called as a slope, okay, which is constant in the earlier case as given by 15 by that is 2 divided by 15, 2 divided by 25, and it remains constant, and that the slope remains the same, and thereafter the slope becomes equal to 0, exactly like the pulse that is shown the voltage. So definitely this is true for L di by dt. Okay, so with so much of inference, let's read the voltage and current waveforms for an element as shown in figure. The circuit element is what? Obviously it is going to be L di by dt, okay, is equal to VL. Okay, so we have di by dt is equal to 2 by 25, and so if you multiply there, you should get 2. So you see that L is equal to 25 Henry. Okay. Problem 10, we are having a capacitance here, a capacitance structure here where we have 2 in series, and then the combination parallel to a capacitance with epsilon 3. Okay, so and the distances between them is 10 and 10 for the series versions, and for the one which is in parallel with both is going to have all of 20 centimeters as the gap between them. Okay, and epsilon 1 and epsilon 2 and epsilon 3 are 1, 2 and 4 respectively. The area is given as 20 centimeter plates, which means that 10 into 20 happens to be the area of each of these capacitors. Okay, so you can put them all together as is required. Okay, and you can have all kinds of approximations, and you'll see that it's going to be near around. Okay, near around 4.75. So the exact value is 4.72 picofarad. Okay, so it's going to be C1 parallel C2, C1 C2 divided by C1 plus C2, and then you will also have plus C3. Okay, where C1 will have epsilon 1 and C2 will have epsilon 2. Okay, and C3 will have epsilon 3, and you will have D1 and D2 as same 20 centimeters, and D3 will be equal to 20 centimeters. Okay, everything has to be converted to meter, and you will have the areas all the same as equal to 20 into 10 into 10 raised to minus 4. Okay, so finally coming to the 11th problem, two identical coils of negligible resistance when connected in series across a 200 volt 50 hertz. Okay, so omega is coming. Okay, so it draws a current of 10 amps. Okay, so you can get what is called as when they are connected in series, you get 10 amps. So 200 by 10 gives you omega L. Okay, L effective. Okay, when the terminals of one of the coils are reversed. Okay, so perhaps when you reverse the terminals of the coil immediately, based on the winding sense, you are actually reversing the dotted terminal. Okay, so you are having if the early case was aiding, now you are having an opposing flux situation. Then current drawn is 8 amps. So definitely now the current has reduced, which means that we are having more inductance, or the fluxes are in aiding nature. Okay, so you get omega L effective for the first case, or omega L1, let me call it as omega L1 as equal to 200 by 10, which is 20, and in the second case it's going to be omega L2 is the same as equal to 200 divided by 8, which is 25. Okay, so now we are having two situations, L1 plus L2 plus 2m and L1 plus L2 minus 2m. The larger value corresponds to L1 plus L2 plus 2m into omega as equal to 25, and L1 plus L2 minus 2m into omega, the whole into omega is going to give you 20. Okay, so you can solve the both, and you can get what is, and since the inductances happen to be the same, the coefficient of coupling between the two coils can be obtained as m divided by square root of L1 L2. Okay, so L1 L2 being the same, you get it as equal to 1 by 9. Okay, very simple. Okay, so I suppose it is well understood, and you are able to see that interconnections make a big difference. Okay, and there are practical examples where all these elements need to be interconnected together, and we need to remember that when you are having there is an initial status, and thereafter the capacitances share the charge such that the total charge remains the same, unless of course you are having a discharging situation or discharging body to discharge the charges through. Okay, so the constant charge theorem, sharing of charges, how they occur. That is, in this case, it's in the first case we had a series capacitances, and how the insulation resistances are always going to be in parallel, whereas the conducting resistances are going to be in series when they are joined together. And then we moved on to the different the different configurations for a pair of coils, wherein you can have conductive series or no conductive connection, or you can have conductive parallel connection. Okay, at the same time, the inductive nature or the flux nature also needs to be taken into consideration. Okay, so then we moved on to some practical applications for capacitors being interconnected together, especially when you are having pin insulators, etc., such that none of the pin insulators in between, especially the vulnerable ones, break down. Okay, so those aspects need to be taken into consideration, not only in not only in terms of pin insulators, also in terms of the bushings of the transformers, etc. Okay, so another aspect is, of course, the cable that is laid on the ground. Again, the same problem is there, because discharges, etc., spoil the nature of the, and it gives rise to, discharges give rise to a lot of leakage of current. So definitely those things need to be taken into consideration, and so hence the capacitance structure is of prime importance. Okay, just as in the inductive case. Okay, and we also see that we have what is called as a larger current flow whenever whenever the inductances when the mutual inductances gives rise to a situation where we are having opposing fluxes. Okay, so that's also important, because it talks about the general impedance, the total impedance that is presented by the coils. Okay, most of the problems have practical significance, and let me hope that when we go to the sources interconnection, or some of the aspects of source interconnection, the next session, it will be interesting to you. Thank you.